All right, so now we move to the next speaker. So the next speaker is Raimondo Pala from University of Rome. So the title of the presentation is the causal interpretation of panel vector autoregressions. So Raimondo, you have 20 minutes, including questions. Thank you very much.
So I hope you can all hear me fine.
Yeah.
My name is Raimondo Pala, as I was introduced. I'm currently a fourth-year PhD student at the University of Rome Vergata, and I'm really glad to be here. I'm really happy to share this recent work. As the title says, it's going to be about the causal interpretation of panel vector autoregressions. And the premise and the motivation, in a sense, is really kind of easy to understand. The problem is that when it comes to finding causality and having data that is a panel in nature that has some time series characteristics, oftentimes we may face some problems. In particular, there may be trends or seasonalities which may be overlooked by traditional methods. When using panel data, the common solutions are to make use of difference in difference, maybe instrumental variables. So if you take the difference in difference case, oftentimes it may be that some data is strongly autocorrelated. It may have unit roots, and there are no methods of implementing such characteristics in the traditional methodologies. So what ends up happening is that, say that you have an intervention in 2015, you have data that starts in the early 2000s, it ends in 2020. What you may want to do is try to avoid the period that goes from the early 2000s to 2010, because maybe that period has some seasonalities, has some time series characteristics that you want to ignore and avoid kind of framing in a time series fashion. So this is a problem. It's one of many problems which can be found when making use of panel data. And so the idea of this paper is to remain agnostic about whether those solutions are appropriate and to try and give a definition of the causal effects that can be identified using panel vector autoregressions. And then maybe the future literature can try and evaluate which method is better in terms of understanding which method fits the data and the narrative better. So there are going to be two focuses here. One is going to be the distribution of the policy. As you can imagine, the distribution of the policy is really influential to understand whether the kind of causal effects that we are identifying are appropriate. And also another particularly important element is the assumptions that the researcher is willing to put on the data structure. So this is going to be kind of a preview of my result. I will be distinguishing between whether a policy variable is homogeneous or heterogeneous. If a policy variable is homogeneous, I mean a policy variable that is the same across units for a given time. So maybe you're trying to find what is the effect of fiscal policy, but all countries kind of agreed that the fiscal policy was going to be the same. Then there's no more information that I can get from a panel vector autoregression compared to the one of a vector autoregression. And I will show that this result matches the one of vector autoregressions of Rambach and Shepard. But in the case of policy variable that is heterogeneous across country, all of a sudden you can find a wide range of causal effects depending whether it's a dummy, whether it's continuous, and the assumptions that you're willing to put on it. So the first kind of thing that I'm obliged to do is to present panel vector autoregressions in this framework. So what I have in mind is, say that you have a set of policy variables that are indexed by K. So maybe K indicates whether it's fiscal or monetary policy. And of course, IT indicates a region or a country at a given time. And then there are going to be outcome variables. These may be GDP or unemployment. And then they will be indexed by J. The classic approach of panel vector autoregressions is to put all those variables together and then to estimate the system. Now, you may see that I'm using kind of weird definition here because I'm defining the disturbances as X tilde. That's because I want to trace the innovations with respect to the original variable and give a definition to the causal interpretation of the innovations. So you estimate with GMM, GLS, whatever you want to use, you get the disturbances, and then generally the way that we want to get causality from a panel vector autoregression is to consider those disturbances and try and find an identification procedure. So the most common one that is used by the literature is the Cholesky decomposition. But to kind of give a link between the Cholesky decomposition and what the causal effects that may be identified are, I'm providing here an example that makes use of a bivariate X tilde IT. So this may be indicating fiscal policy on the first variable and maybe GDP on the second variable. What you do is you take this gamma to be the division between 012 and 011. which is basically the covariance of the innovation of fiscal policy and the innovations of GDP, divided by the variance of the innovation of fiscal policy, because this is rescaled by the first element. So what is the causal interpretation of this? Well, a causal interpretation in the classic macro sense is a dynamic causal effect. It tells me what would be the value of output under fiscal policy being, say, a high amount versus fiscal policy being equal to a low amount. So say that this is a high amount, the first W is a high amount, and the second W, the W prime, is a low amount. So one measure of how all the system influences my outcome variable is this one. It's basically the same definition that was provided by Rambach and Shepard, and it's telling me that the impulse horizon of the output depends on the distribution of the policy variable. The previous values of the policy variables is the first element. All the other policies, so maybe monetary policy and other policies that are not the fiscal one, are also going to be in this definition, but also it's going to be the specific value of fiscal policy. And then finally, the future value of all the other policies and fiscal policy itself. Now, the four kind of causal effects that I'm going to be discussing are the following. Average treatment effect will be indicating the difference in expected value between, say, output under fiscal policy being high and fiscal policy being low. An average treatment effect on the treated tells me the same kind of information, but on the subset of times that are identified to be one that are treated. And an average causal response provides me a lot of information about the slope. So basically tells me what is the effect of tiny changes in a given value of fiscal policy that I'm here calling lambda on the output. And then an average causal response on the treated is again the same, but under the conditioning argument that a time has been extracted to be one in which the policy is equal to lambda k. Now, I told you that the first result was going to be resembling the one of Rambach and Shepard. I defined what a policy variable that is homogeneous is. It's a policy variable that is the same on across units at a given time. So maybe there has been fiscal policy in a given country, all the regions are either treated or controlled. What can we do? Well, the intuition here is I'm going to first bind the distribution of the policy variable to be telling me that either all countries or regions are either treated or controlled. So if a region is treated with a probability 1, then it must be that all the other regions are not treated with probability 0. So they're all treated at a given time, or they're all controlled at a given time. How is my counterfactual being generated? From the forecast error. And that is, in a sense, a really underwhelming result because I need to put a lot of independence assumption on the policy variable. So my second assumption here is going to be required in order to get a causal effect. In particular, I'm saying, okay, the innovation of my policy variable are required to be independent on the past, on the other policies, on the future of the policy, and on whether the policy has been changed in order to change output, which is a really credible assumption. So basically, what I'm going to show here is that gamma is taking the difference between GDP or output under the fiscal policy being a high regime and the fiscal policy being under low regime. Now, I can decompose both of these arguments into the potential outcome framework and the selection bias term. And the selection bias terms are grouped in this delta here, that's below. So when is it that this delta is going to go to 0? When those arguments are going to go to 0. And those arguments are going to go to 0 in the cases in which the innovations of the fiscal policy are exogenous with respect and are independent with respect to all those different kind of variables. And that is what the second theorem is telling me. Now, the idea was, let's try and see whether panel vector autoregressions can tell me a lot about causal effects. But here, in order to get a causal effect that is interpretable, I'm requiring all those independence assumptions. But panel vector autoregressions can have a lot more information than the one of a vector autoregression. So in particular, what I'm going to be discussing now is a system that resembles the one of difference in difference, in which I have that some units are treated and some units are controlled. So the fact that some units are treated and some units are controlled can be put in terms of a very simple assumption in terms of if I have that one unit is treated, then it must be that all the other units are non-treated with probability, are treated with probability 0, which means basically binds the distribution of W to be so that fiscal policy is high for some country and low for some other country contemporaneously. And if there's a kind of randomization among whether some countries are treated and some countries are controlled, then I can work with that and find some assumptions that allow me to find a causal effect. In particular, I'm going to require two assumptions, which are resembling, again, the one of the difference in difference literature. The first assumption that I'm going to say is that the treated units, if they were to not be treated in a treated time, they would have been the same as the non-treated units. In a sense, it's really simple to say, well, if the country didn't receive a high value fiscal policy, they may have been the same one that I'm observing for the other ones under a non-treatment of fiscal policy. And the no-anticipation assumption is the same one, but on the periods that are not treated. And under those two assumptions, I can give an interpretation to my gamma. So remember, my gamma was the covariance divided by the variance. And so in this case, I can rewrite my gamma to be identifying the difference of four cases: the units that are treated, the units that are not treated, times that are treated, times that are not treated. That is what this gamma is telling me. And all of a sudden, I can plug in the no anticipation and parallel trend condition, and I can get an average treatment effect on the treated. Now, usually, from the causal literature, average treatment effects on the treated are are considered to be less relevant than the classic average treatment effect. But in this case, I'm getting an average treatment effect on the treated without relying on this wide range of independence assumptions. So I'm still getting a causal estimate without requiring all those independence assumptions to hold. Now, finally, there is going to be another case, which is also kind of an optimistic case, in which I can get causal effects by using some units as control for the others. That is the case of a continuous distribution of the policy variable. So say that some countries receive a high value fiscal policy, some receive a medium high value fiscal policy, and so on, in a continuous fashion, and that the distribution of the fiscal on the innovation of fiscal policies is normal. By the means of this kind of narrative, I can generate a world in which I'm getting a lot of information about what would be the effect of changing fiscal policy by a tiny amount. Now, the problem is the following. This is a really nice quantity to get in the end, but if you don't have the distribution is normal, then it becomes really tricky to give it an interpretation. So I'm going to require two assumptions in this case. The first one is about the continuous differentiability of the forecast error of my outcome variable. And the second one is about the fact that my fiscal policy in its forecast errors is still required to be normal. Under this scenario, what I can do is, remember, my gamma is a covariance divided by a variance. I can rewrite this in terms of expected values. Those expected values can be rewritten in terms of an integral. And then I can show that the integral is going to depend on two quantities. One is the first derivative of what I'm calling here G, which is the conditional expected value of the forecast error of the outcome variable under the policy variable being equal to a given amount. So this may be indicating the conditional expected value of GDP under fiscal policy being equal to a given amount. And then a set of weights, which I'm here defining Q. And it turns out that the normality assumption is required in order to make it so that those weights make gamma match the definition of average causal response on the treated. So this is a really nice result. It makes a lot of sense that you can get such a really important quantity from using the normality of the distribution of the policy variable in its innovations. However, as I said, deviations from this normality assumption can be really harmful. So a common case that exists in the empirical literature is the one of still a continuous policy variable, but it being non-negative. It's the classic case of Callaway, Santana, Goodman, Bacon. It doesn't go under the non-negative narrative. It goes under the continuous treatment narrative, but it's basically the same. So this case, for me, is going to be a really negative one. For them, it's partial because they can still give it a little bit of a causal interpretation. But for me, it's negative because remember that those are the forecast errors. I don't have much control over their distribution. So the two assumptions that I'm going to require are still the continuous differentiability of my outcome variable, my forecast error of the GDP. And I'm going to say my forecast error of the fiscal policy variable is non-negative. Under this scenario, what I get from my gamma is still the same quantity from before. This is still the ACRT from before, which is multiplied by a set of weights that are Q1. But there is also an average treatment effect here, which is rescaled by the lower element of the integration symbol of the first quantity. Now, if I have that the distribution of this is still normal, then I get back to the ACRT. If I get that this is a purely dummy, then I get back to the average treatment effect, However, I'm halfway in between those cases, and I'm getting two quantities on a coefficient. So in a sense, for me, this is going to be really negative. And you can see here that in order to get a unique interpretation of my gamma, I would have to either have the Q1 is equal to 1 or the Q0 is equal to 1. So just to recap the results that I've gotten here, the first result was a really negative one. I started from a world in which panel vector autoregressions give me the same information of vector autoregressions. I had a dummy policy variable, and I required all this wide range of independence assumptions, which are really difficult to satisfy. Then I said, okay, maybe there are some units that are treated, some units that are controlled in the same time. I can use the units that are not treated as a counterfactual for the ones that receive a treatment, which is a really positive result. Those went under the parallel trend and no anticipation condition, and I've shown that this becomes an average treatment effect of the treated. However, in the scenario in which there is a continuous of units which receive different values of treatments, and this distribution is normal, I've shown that it becomes an average causal response on the treated, which is a really nice quantity because it can tell me what is the effect of a given change of fiscal policy on GDP. But if this distribution is not normal, as in the case of a distribution that is cut at 0 and only goes to positive values or 0 values, then kind of hell breaks loose because I don't control what quantity I'm getting here. So if you have any questions, if you have any considerations, if you have anything that you would like to tell me, feel free to do so. And that was my presentation, and I hope that you liked it.
Thank you very much, Raimondo. So let me stop the recording.